So just a quick overview of the agenda. We're just going to be talking quickly about the previous work we've done with TEs involved at Meta, the new CVM platform we've built, some attestation components we've added associated with the CVM platform, some trade-offs / challenges, and some use cases / future work. And we'll probably have some time for questions afterwards. So recently, this year at Meta, we've had an increased investment in TE technologies, most notably in AMD SEV-SNP. Now, we, the TE Infra team, are focused on building infrastructure to help enable application lift and shift for service owners at Meta to onboard their products into CVMs. The primary use case we are focusing on is defense in depth. Now, this is just mostly focused at a security viewpoint, where the idea is we want to prevent unrestricted, unprivileged access to high-level secret or high-value secrets at application memory and runtime. Now, to give you a little bit of context, at Meta we have over thousands of services in our ecosystem, each owned by different teams, operating at varying levels of security and criticality, and in various areas in the world, possibly in POPs or in data centers. And most notably, we share a lot of these a lot of the services are sharing the same host. And we want to prevent any sort of misbehavior from these hosts or these programs by enforcing some sort of VM isolation using the confidentiality and integrity guarantees we get from CVMs. Now, we want to do all of this while using relatively cheap commodity hardware, and that's where something like CVMs come into play. Now, previously, last year, we've talked about securing Meta's secrets on edge using SGX enclaves, and the challenges associated with using SGX for development. Now, we found at Meta that application lift and shift in using SGX wasn't very practical, namely because of the restricted runtime you would get. Because of this restricted runtime, we actually had to bifurcate all of our applications that want to use SGX into trusted and untrusted components. And this required a high amount of dev effort to do so, and required both expertise in SGX and the application itself. And furthermore, whenever we did a transition in and out of the enclave for computing a syscall, this would incur a non-trivial amount of latency. So for all of these three reasons, we decided we should we didn't end up adopting SGX very much at the company. However, with CVMs, we don't have this restricted runtime, but we can still enjoy some of the similar security benefits we could get from TEs. So if we look at this CVM platform here, this is something that we've built out where we have built-in runtime infrastructure to enable application lift and shift. The idea here is that service owners at Meta don't really care about injecting TE dependencies into their applications, but rather they just want to run their services as usual, but with additional confidentiality integrity guarantees. So the idea is we provided a wrapper which enabled service owners to embed their applications into a VM image, which also contains some other components that my partner will talk about, and deploy these in a container, which is just the standard unit of deployment at Meta. The figure on the left is just the additions of what we do with the CVM platform, and the figure on the right is just a standard application deployment at Meta. So we should talk a little bit about remote attestation. I think you've heard a lot about attestation at this conference already, but it's an essential piece to the puzzle for CVMs. Meta is in this really unique situation where we are simultaneously the cloud service provider, the attester, and also the relying party, which means we can do kind of very interesting things with our attestation story. But we need to be able we need to answer the question of how should we support this remote attestation internally while also integrating with existing Meta infrastructure. And we have to make sure we do this in a way that's scalable as well. So before we go into that, let's just go and walk through a relatively naive example of an application level remote attestation. I'm sure most of you are aware of how this works, but just to elaborate on our example, we're just going to go through a very simple protocol. So we have a CVM application and a relying party, and the CVM application wants to acquire some sort of shared or confidential resource. So what it'll do is generate a private public key pair. It will embed that into the attestation report and make sure it's cryptographically bound to the attestation report. It'll then pass it to the relying party through some sort of RPC, and afterwards, the relying party will have to do two things. First, it'll have to make sure that it's a valid attestation report, and that is the attestation report was signed by a legitimate CVM. So it's going to follow the AMD PKI, validate the attestation report via some cert chain provided by the PKI, and then afterwards it's going to have to verify that the measurements provided are also known to Meta and are corresponding to one of the known policies for this particular CVM. And after it verifies this, it will then go and encrypt this secret using the public key provided and return it to the CVM application. Now, one challenge with this particularly naive remote attestation protocol is that both the attester and the relying parties have to integrate this attestation logic into their code. And as the T-infra team, we could abstract this into a library, but then we'd have to support both multiple languages as well as possibly multiple T technologies. And this is going to be kind of an issue for scaling when we have to do it for many, many languages, for many, many technologies, and also many, many services. One thing that I should recall is that we are running thousands of services at Meta. So if we are trying to incorporate TE technologies or remote attestation into all of these services, it's going to be not scalable.
Right, so the solution we came up is to do this. Instead of doing explicit remote attestation at the application level, CVM applications will be provisioned X509 certificates with an attested identity. They can then use this attested identity to access resources in Meta Infra that may be restricted to only attested CVMs. So here's an example of what this identity might look like in this certificate. The protocol we describe is basically an implementation of the RATS passport model. So when the CVM first boots up, the CVM agent, which is the systemd unit that we embed into every VM image, it will generate a public-private key pair. This will be used for the X509 certificate. Then it will generate the CSR, certificate sign request, and an attestation report that is cryptographically bound to the key pair. It then calls out to attestation service to request a particular attested identity. This could just be any string. The attestation service is basically a registration authority that we own and maintain. So to appraise the evidence, it will first validate the report using AMD's PKI, then extract the measurement and check it against some expected set of measurements. The implementation details of this lookup is hand-waved for this presentation. And finally, it will verify the cryptographic binding between the report and the CSR. So if that checks out, then it will call to Meta's internal CA. Meta's internal CA is the only entity that can mint these certificates. And note that attestation service is the only entity that can request attested identity certs. So now that we have the attested identity, the CVM application can do thrift RPCs to other entities in Meta Infra to request some resource. So it will provide the attested cert as part of the standard TLS handshake. We don't modify this in any way. After the TLS handshake completes, a middleware authorization library will extract the attested identity and check that it has permission to access this resource. If that checks out, then the resource can be securely returned back to the CVM application. And what I mean by that is that TLS terminates inside the CVM. So what happens is the TLS session key and private key are generated and reside in the CVM protected memory. This ensures that the application payload never appears as plain text in the untrusted memory. So by reusing TLS for the encrypted channel protocol, we avoid having to reinvent, redesign, and re-implement an encrypted channel protocol at the application layer, because that would end up with an encrypted channel and an encrypted channel, which is redundant, since thrift already runs on top of TLS. The other benefits of this model is that we reuse the concept of identities in X509 certificates. So as mentioned, this is already a native concept within Meta Auth infrastructure. And this is nice because relying parties do not need to do explicit attestation of CVMs. They can just look at the attested identity in the cert and blindly trust that this entity has been attested, because everybody trusts the Meta CA, which is the only entity that can mint these certificates. And this is desirable because it allows us to scale the solution to support many relying parties in our massive ecosystem. On the other side, the application that will run in the CVM does not need to be aware of the runtime environment. So it doesn't need to care whether it's in a CVM, a VM, a bare metal, a container. And this is desirable because then service owners do not require deep technical knowledge about attestations or CVMs. And there should be very little development effort for them to onboard their applications to use our CVMs. And finally, one last side benefit is that the CVM is attested once, compared to the more naive protocols where you might attest for every RPC, or maybe you attest once at the beginning of a session for each peer that you connect to. So by testing once, we avoid a lot of unnecessary traffic, and we just keep things simple. So here are some of the challenges and trade-offs we encountered when working on this. So although CVMs allow for the convenience of lift and shift, it does trade off for larger TCB because now we are putting the entire application plus middleware layer into the CVM. And this is not desirable for some use cases that care about proving code provenance to auditors. They desire a minimal TCB. The other issue right now is that we have some build time overhead because service owners need to build entire VM images as opposed to just the containers, which are the standard unit of deployment here. And our build system is more optimized for containers than VMs. We are working on this so that service owners do not have to build the entire VM image. And finally, we noticed that there is some latency and throughput regressions compared to standard container deployments. And this is expected because SNP has some baseline CPU memory network overhead. So to wrap things up, let's talk about some of the future work items we have planned. The scope of our team's work continues to expand, and we are onboarding more and more use cases internally every quarter. So one item is deploying applications with the CVM sidecar. So the main idea here is we partition the application into such that only a small amount of critical code runs inside the CVM. And that will run as a sidecar beside the main process. This is very similar to how SGX enclaves are deployed. We've come full circle here, but the trade-off here is we lose lift and shift, but we have a slightly smaller TCB because at our company, the application and middleware layer is a lot of code. Next, bitwise build reproducibility for VM images. We are looking into containerizing the build process such that VM images are built and we can eliminate the operating system sources of non-determinism. The goal here is to reliably produce the same VM image bit for bit from a source provision. And this will help us demonstrate to auditors and for use cases that care about code provenance. Also, confidential micro VMs. So micro VMs are a nice compromise between containers and virtual machines because they provide stronger isolation guarantees than containers, but they use less resources and have less startup time overhead than typical VMs. And combining these properties with confidentiality would enable us to unlock some really exciting use cases, maybe related to Gen AI. So there's a couple more items to talk about, but we don't actually have time for that. So some closing remarks are that we are excited to continue working on developing trusted execution technologies at Meta to improve the security and privacy guarantees of our vast service ecosystem. Thank you, that is all. Any questions?
Hello, so I'm David. I'm a PhD student at Berkeley. I was just wondering, so if you don't have build reproducibility for VM images right now, how are you attesting that you are actually getting the VM you expect? Because I assume you have to hash the image and compare that to an existing hash you have, right?
Right. Yeah, I guess I can take this.
Oh, yeah, go ahead. Yeah.
Oh, yeah, sure. Yeah, so this is a particularly unique situation for us because we own like kind of the, so like as I said previously, like we are simultaneously like the attester, the cloud service provider, and also like the lying party / verifiers. So for our purposes, like we kind of implicitly trust our build chain. So whenever we publish a measurement, we assume that it was built in our own proper ecosystem. So that's part of our threat model assessment. But you're right, like for build reproducibility for various deployment models, especially those involving open source, we do need to work on this. And so that's something we are going to heavily prioritize in the future.
Cool, thank you.
Hi. Thanks for the presentation. I was wondering, the system you described sounds similar in some ways to Spiffy Spire for doing workload identity, but it seems you chose to integrate it at the Thrift RPC level more. Can you talk about why you made that decision and those trade-offs?
We integrated what at the Thrift RPC level?
As opposed to doing something like adopting Spiffy Spire directly, it seems like you've moved a portion of the work into the Thrift RPC layer of unwrapping the attestation.
Oh, I see. So you're talking about how we look at the attested identity, but not in the TLS handshake. We do it at the middleware layer, right? Okay, so yeah, while it was possible, I forgot to mention this, but yeah, while it was possible for us to do it at the TLS handshake layer, we found that we have better error handling and observability in our infrastructure if we just do it at the middleware layer. Because if something goes wrong with TLS, then it's kind of hard to propagate what exactly went wrong in the handshake. And we don't own the TLS code at the company, like another team manages that, and then working with them, it was suggested that we don't embed it at their layer.
Okay, got it, thanks. I had a second question. So do your relying parties, how are your relying parties defining which workloads that they trust?
Okay, yeah, right. So the relying party sees what we call the attested serves identity, which is just like a string. And then the string will map to a policy that we store somewhere. It's a trusted database for all that matters. And then the policy might describe things like what TCB, what measurement this VM is. So basically, only certain VMs with a particular measurement can obtain this identity. And then as a relying party, you would say, okay, I trust this CVM with the keychain identity.
Yeah.
Okay,
Hope
thanks.
that answers it, yeah.
That helps a lot, thank you.
Yeah, and just I guess if you want to map it to some particular standard that's out there, it's like essentially an implementation of the RATS passport model.